Hi everyone, this is a test 2 continuation of the delayed lens effect in a transformer here that I've been testing. That's the same setup that I have from test 1 video, and we're exactly at the same frequency here as well at 4.9 kilohertz, which is a very high frequency for a microwave oven transformer. So what I decided to do is attach a LED here to it, and the LED does pretty much the same thing as if you had a short. There it is with the LED disconnected, the waveform, and there it is with the LED connected. Or here is a short circuit. So short circuit off, LED connected. So it's pretty close to a short circuit itself. So we're going to use this LED to continue the test. So now I've disconnected the LED now, and what I'm going to do is I'm going to drop the frequency of the signal generator down lower. And if you can see now, see here we were up here, and the green line here, this waveform is our current being used. Now when I drop that down, look how much the current drops as well. So what I'd like to do is right here, see that area right there where it's utilizing the less current as possible? And if we look at that frequency, we're down to 2.4 kilohertz, so 2,400 kilohertz. That's about our flattest on the current curve there. So here, what I'll do now is I'll attach my LED. So the LED now is much brighter actually, probably about twice the brightness. But if you look at the current is very high. There it is disconnected, and there it is connected. Now what I decided to do is to start experimenting maybe just quickly with capacitors. And what I've done is I've put some extra wires here on the primary of the secondary. This is the primary. And I have here the two leads coming. And here I have a 0.39 microfarad capacitor. Unfortunately, the light condition is not very good in the boat here. Anyways, I've measured it with my capacitance meter. And you can believe me that works well. So we'll disconnect our load. So we're down flat there, as you see, for the current. And we'll connect this capacitor here. So our capacitor is connected. Now it actually consumes a lot of current with that capacitor connected. But now let's connect our load. Now our load is connected. Same brightness as we had before, but look at our current. And now what I'll do is I'll just fine tune it right there. So right there we're using the less current, much less current than our previous test before. If we look at what we're using there, we're measuring about 10 millivolts RMS across that 1 ohm resistor. So that's quite significant there. So now if we disconnect our capacitor, there's our current that jumps back up, and there is the data on that as well. And now if I disconnect the load, we're back down to just the idle current that the transformer is using with no load connected and no capacitor connected. So basically by adding a capacitor in parallel, sorry about the moving of the camera, by adding this capacitor in parallel to the primary, I'm able, when there is a load or even a short circuit, to drop the current by finding the right capacitor anyways, to where the primary would be exactly consuming the same amount of current, just idle, just nothing happening, just like it is right now. So there you go, showing you that. and connecting the load. Again, the current is up, and now connecting the capacitor, and it's back down again. So there's our LED, very bright, full brightness, and I just thought that was kind of interesting and thought you'd like to see this. Now the other thing that I'm going to do in this video here is, now that's a 0.39 capacitor, 0.39 microfarad, and I'll connect here this is a 6.8 microfarad, to see how low we can drop the current. So now I've connected that. Our LED is pretty well extinguished, hardly any light coming from that. Our current has shot up, but what I'll do now is I'll drop down the frequency. So now I'll switch my signal generator, and I'll have to step down the times division there so that we get a better view. And now, as you see, when I tune my signal generator, again, there is the ideal setting right there. So the current is now not as good as the previous frequency, okay? We're down at 27 millivolts across RMS, across our 1 ohm resistor. But we're down now to frequencies, that operate usually better possibly in these transformers. So we're down to 581 hertz there on that particular frequency. So I thought this was kind of interesting and worthy of sharing. And as you can see here, I am bringing the frequency up, and here I am bringing the frequency down. And as you can see, you can have the phase shift happening, but obviously it's taking less current when both of them are aligned. And our LED is super bright right now, actually even brighter than it was at the previous frequency with the 0.39 microfarad capacitor. So again here, if I disconnect my load, the current shoots up. But now if I disconnect my capacitor as well, so now it's just normal idling transformer, there is what the current uses. So I kind of like the previous thing happening with the 0.39 because that was a point where naturally that primary of that transformer idled and had a lot less current use just for idling. So I'll flip it back and we'll try to find that spot there. And now I have to change my times division here. And here we are. So there's that spot there where that current has that nice flat area there. And now if I attach my 0.39 to that, and our LED, again, now we just fine tune and we can get the same very, very low power consumption there. Pretty well just like if that transformer was idle with absolutely no load on it. But yet we have a load, the LED here, which is pretty well at full brightness. Not quite as good as the lower frequency. We're at the 2.45 kilohertz here, but at the 500 range frequency we had with the 6.8 microfarad capacitor, the LED was obviously lighting more. So anyways, thought I would share that is an interesting effect there, and probably worth studying a little bit more. So go ahead and post your comments, and thanks for watching.